So in addition to loop optimizations, you can also work on procedure or function level. So calling a very short procedure is always very expensive because you have to save context, you have to save parameters somewhere, then you have to execute a call instruction, then this function is executed, and then you return from this function. So if you have a short function like our function foo, which just calculates a plus b minus c, just given these three input parameters, and returns the result, usually we would call it that way, which would mean we would need to copy w, x, and y into the registers that represent a, b, and c, or even on the stack, depending on your processor. Then it would have to calculate this expression, it would have to assign this return value to whatever is in z and return from the function. So this is obviously quite a bit overhead for just doing an addition and a subtraction. So obviously by just doing variable replacement, you can copy this instruction over here. So z equals, well, now you have to replace the variables here. So you have to replace a by this formal parameter w, you have to replace b by this formal parameter x, and you have to replace c by this formal parameter y. So you can just replace this assignment here by z equals w plus x minus y. So it's just maybe two machine instructions and no function call, function return, and register copying overhead. A programmer can ask the C compiler to inline a function. C provides an inline keyword, but the compiler is not required to honor this function. So inline nowadays is a hint to the compiler that it can inline a function, but a compiler has many heuristics actually that help it to decide if a function should be inlined or not, and usually this is better than a programmer intuition can provide. The compiler also can inline functions itself without indicating it using an inline keyword if the compiler thinks this would be useful. So we've already seen function calls can be costly. Arguments and results need to be passed on the stack or in registers. We have to call and return instructions. We probably have to flush the pipeline. We have to take care of our stack frame and so on. So essentially, these are direct costs. We also have indirect costs because we are switching to a different basic block. We are breaking intra-procedural analysis because we need to analyze data and control flow between procedures now. So this makes it more complex and more difficult. So inlining removes these costs, but of course we are copying a function to all the sites where this function is called. So this increases the code size. This can reduce the instruction cache hit rate. So again, it's not an optimization that helps in any case, because otherwise you just inline all functions and be happy. But obviously that's not the way to go. So one thing that's always necessary when writing code for an existing machine is to do register allocation. So registers are the fastest memory your computer can provide because they're integrated in the CPU. They're a part of your data path in your CPU. So when you access registers, there is no latency for accessing them. It can go with the full bandwidths compared to accessing caches or external main memory. So of course it makes sense to keep exactly those variables in registers that are used very often. So essentially this means you would reduce the number of memory accesses here. Good register allocation so is key to performance because memory accesses are costly, and compilers analyze the so-called lifetime of variables to do register allocation. So programmers were able to hint which variables to keep in registers. C has a special keyword register for it, and that was used extensively in early 1970s Unix implementations where code was small and programmers really knew which variables were accessed more often. Modern compilers accept this keyword and just ignore it because they usually know better than the programmer which values to keep in registers. Some variables always need to be in memory instead of registers, so you've probably seen the volatile keyword before. Volatile means that you can't optimize a memory access to a variable away because it might be a memory mapped IO register. So if you just continuously read a status from a memory mapped IO register in a loop, which is just standard polling method, for example, waiting for a character to arrive from a serial line, Your compiler would just figure out, oh, the value of that variable never changes because it doesn't know there's a piece of hardware that can set a bit in that variable, and it would try to optimize this access away, resulting in an endless loop, just waiting for something that never happens. So the volatile keyword tells the compiler, really try to avoid any optimizations, try to avoid keeping this value in the register, and always when a read operation or write operation on this variable is done, do a real memory read and write operation. For a RISC architecture, of course, to check a value of a variable, we still need to copy it from memory to a register, but we need to do it all over again when we have to do the next read or write access to that variable. So volatile is especially important when writing device drivers, implementing semaphores in memory. So any condition where something might happen that your compiler can't know about, like hardware functionality or a parallel process that's executing and using the same shared memory region for doing synchronization. So register lifetime analysis just checks, yes, how long a variable value is actually needed during the execution of your program. So for example, you have these three instructions here: w equals a plus b at time 1, x equals c plus w in time 2, and y equals c plus d in time 3. So we see that variables a and b are only used in the first instruction, so we don't use them afterwards. Variable c is used in the second and third instruction. Variable w is written in the first one and read in the second one, so we have its lifetime here. Variable d is only used in the first instruction, so that might be its lifetime here. And variables x and y are only used in their respective lines. Of course, you have to consider this in a larger context of a control and data flow. So essentially, variables coming in already have some lifetime before, variables going out, so being assigned to have some lifetime afterwards. But that diagram here just captures this moment of the three lines. So now we can do register allocation for our very simple example here. And the way to do it is a way that's a standard algorithm for many problems, which is called graph coloring. You maybe have heard of this famous problem of coloring maps of countries. And the question is, how many colors do you need to color any possible map? And it took like a century to do a proof that the number of colors is actually 4 that you need. Graph coloring is a very similar approach. So you actually connect your variables in a diagram representing your data flow. So which variables depend on each other. So A and B depend on W and on X and C, and so on and so forth. And now you try to assign each node of your graph a different color, so that there are no two neighbors with the same color. But of course you can reuse colors. So essentially, if there's no direct edge between this variable w and y, you can reuse the color here because you don't have a direct edge between them. So essentially they don't interfere with each other. So edges between variables indicate that these variables are live at the same time, so they would conflict for the same register. So A, B, and W, for example, are live at the same time, or C, W, and X are live at the same time, or back here, Y, D, and C are live at the same time. So if these variables are live at the same time, we can't reuse a register for storing Y and C, just because, yeah, otherwise we just override one of those values when we assign the other variable. So that's what we model here. And then by coloring our graph, we can actually assign each register of our processor with a separate color. So if we manage to color our graph with only 3 colors, we know that we need 3 registers: a blue one that keeps A in step 1 and C in steps 2 and 3. We need a green one that can keep variables B, X, and D. So B in step 1, X in step 2, and D in step 3 here. And well, the same for W and Y, obviously, which are only used in step 2 here. So we color the nodes with as few colors as possible. No edge must share color. And so we get this allocation, and then we can assign colors however we want. So A would be assigned to register 0, and the same would happen to C because it has the same color. B would be register 1. Green is also the color of X and D, so X and D are also assigned register 1, and the brown ones are assigned register 2. Now the problem with this is NP complete. So this is a really, really hard problem to solve. So essentially you can't find a really optimal solution in a time that you would want to accept for your compilation to happen. So compilers usually use heuristics to reach a good solution. Of course, compilers need to ensure that they don't doubly allocate two variables to the same register at the same time, because then you'd have very, very subtle errors that are very hard to find. So essentially there are more improved approaches for register allocation, and we'll cover them in our compilers course. So now one problem when you do a register allocation is that you can change the scheduling of instructions. So if instructions are not dependent on each other because of data flow dependencies or control flow dependencies, you can shuffle them around in memory, so you can move one instruction before the other, even if your compiler generated them in the other order, just because your code might be more optimal. This will change the number of registers required because it changes the lifetime of your variables here. So if you have these 4 instructions in this order, you can do this as an exercise at home. You can figure out that you need 5 registers to implement that code. Now if you change them around, just considering the data flow, so this is still a valid execution of the code, just with switched around instructions, you'd only need 3 registers. So depending on your instruction scheduling, this might also help. So again, as we've seen with several optimizations before, these optimizations interfere, like instruction scheduling and register allocation usually have to be done in combination in order to get a more optimal result out of it. Now, the final thing we have to do is to select instructions. So intermediate representation code is already a very low-level code in many cases, so the instructions generated for IR are very close to machine level, but they are not machine instructions. And so depending on your target instruction set architecture, you really need to figure out which instructions of your machine correspond to which intermediate representation instructions. And in some cases, you can combine some IR representation instructions to one machine instruction, or the other way around. You have to split one IR instruction to several machine instructions, so there's not always a one-to-one correspondence between these. IR instructions, as we've seen, are represented as control and data flow graphs. So essentially what we do is we have templates for expressions. So for every possible expression in our intermediate representation, we can find out what machine instruction would fit best here. And depending on your cost metric like performance or energy, this template should fit best. So there might be different templates for your different optimization strategies or optimization objectives you want to apply to your generated code. So for example, we have an expression here that does a multiplication first and then an addition. Well, we can check for templates. So we have an IR multiplication that might be represented by a mul instruction in your instruction set. And we have an IR addition operation that might be represented by an add instruction in your machine code. But if you have something like DSP instructions, for example, in ARM Cortex M4 or similar, you might have one instruction joining a multiplication and addition. This is very common in digital signal processing, for example, and you could just have another template that says if you have a structure like that one on the left-hand side here, you can replace both IR instruction by a single multiply and add instruction, which of course executes faster than 2 separate mul and add instructions. So the final parts of our compilation toolchain are discussed now. So first we have an assembler. So the assembler takes your assembler machine, human-readable source code of machine instructions and generates the real binary machine instructions your processor is able to understand and generates the object relocatable object code file, the O file. So an assembler is very simple compared to a compiler. So in general, you can write a very simple assembler by just applying a table to map the human-readable instruction names like add to their bit patterns, transforming their parameters into another bit patterns, and putting these bit patterns together to form, for example, your ARM machine instructions. So it generates machine instructions in binary representation from our symbolic assembly code, and it's usually a one-to-one translation. But assemblers can do more, because you don't want to have magic numbers like branch offsets or something represented as numerals in your code. You want to have something like labels. A computer wouldn't really need these labels, but for a human trying to read this code, this is very helpful to know that it's not address plus 47, but it's a label end of loop that it's being jumped to. So labels are translated into addresses because branch instructions only understand relative or absolute addresses. You can have pseudo ops, like defining that the following instructions are text, so program text, or maybe data elements like character strings that have to be put into memory. Some processors also have pseudo machine operations that make assembly programming for humans a bit easier if you have to do assembly programming by hand. That depends on your processor architecture, so then the assembler would have a slightly higher level of abstraction than your machine code. And very often you use a two-pass approach. So in the first pass, you figure out all the symbols, so where your data is located, where your labels for branches and so on are located, and generate a symbol table. And in the second pass, whenever you translate each single instruction and it references such a label, you just reference the symbol table and replace the symbol name by its numerical value to put into the instruction. Then you can generate machine instructions. So, for example, we have some high-level language code, and on the right-hand side we have ARM assembler. So we have two variables, int a and b. So essentially, these variables would be stored in a memory region that starts at address vars. So this is indicated by the equals vars parameter here. This is a pointer, which is loaded into register 0, and then variable a is at offset 0 of that variable, so it just does an indirection of R0. So it loads memory from the address R0 points to, loads this into R1, so this is our value of A, and since an integer is 4 byte on a 32-bit ARM, it adds 4 to R0, so it just indexes the next variable here, it adds 4 to the pointer, and loads this value into R2, so this would be our value for B, and then it compares the two, so this is our comparison operation while A is not equal to B. So again, we have the inversion of our condition here, so we compare and then we branch if equal to the end because we want to branch over the loop, whereas the while loop, when the condition is fulfilled, jumps into the loop, so that's why we have to invert the condition here from not equal to equal. Then we have our assembler translation of a loop body, and at the end of the loop we jump back to the start of the loop using this branch instruction, and otherwise when this loop is ended we'll end up here after the loop. So generating the symbol table now means we go over assembler code and scan our file to collect all the labels and their addresses. So addresses are usually relative to the first instructions in the file. So we want to have relative addresses instead of absolute addresses in memory, but there's also ways to specify absolute addresses for things like reset vectors, interrupt vectors, which you might need when you do bare metal programming on an ARM Cortex microcontroller. So starting with our symbol table, we would have two symbols here for loop and for end. And each ARM machine instruction takes 4 bytes. So the first is at offset 0, the second is at 4, the third is at 8. So the fourth here with the label loop is at address 12. So the label always indicates the address of the following machine instruction here. 12, and then of course we don't know how large our loop body is, so let's just assume the end label would indicate that the following instruction, which we didn't give here, would be at address start plus 28, and start is just the address of the very first instruction here. So what we can do now is we substitute the labels in our code with addresses, so we branch to end and we branch to loop. So we'd say we branch to start plus 28, which is down here, or we branch to start plus 12, which is up here. So this is our assembler that has replaced our symbol table information by the numerical relative address information here. Now what happens if a label is defined in a different file? So for example, we have some add operation here at label 1, and then we branch to label 2. And this label 2 is in a second file, so your assembler can't find it, right? That is the entry point of the function, which just does some additions, but since, like a C compiler, the assembler treats all of the files separately, it doesn't really know where label 2 actually exists. So it's treated as a so-called external reference. So the assembler takes note in the object file that there's something called label 2, which it doesn't know what to do with, so it's left for the linker to actually handle and replace this. So this external reference needs to be cleared up, needs to be resolved, and this can't be the task of the assembler because it doesn't have the global view of all the assembler files in your project. So the linker has to do it. So the assembler generates an output file. This is a so-called object file. There are several standards for this. Like most Unix systems use the so-called extended linking format, ELF. There's another format, the extended common object file format on Windows called ECOF, and Mac OS X does something different. They use a format that's derived from a research operating system called Mac, and it's called Mac-O for Mac Object Format. And these object files include obviously your program code and your program data, your symbol table, all the information about parts that are relocatable in memory, all the external information, of course, which stuff could not be resolved here, and possibly debug data, so information about which memory address might resolve to which variable in your C code, so you can do some source level debugging in GDB and so on. So references to, for example, your C source file if this assembler code was generated by a C compiler initially. And so if you have several object files generated either by a C compiler, via an assembler, or directly via assembly source code files, the linker now takes all these object files, has to figure out how to put them together in memory, has to resolve all the external references between the object files and from the object files to some libraries, and finally generates the executable. So it takes multiple object files and libraries, all together generates one executable files, combines all the object files together, so all your program code in your text segments, all your data in your data segments, figures out start addresses for all modules, because we know this has been relocatable before in object files, so now they're assigned to memory addresses. Then it combines the symbol tables, and in the combined symbol table it tries to figure out if all the symbols can be assigned values. If not, it throws an error like whatever symbol is not defined anywhere, so it can't link an executable program. It transforms relative addresses to absolute addresses and then generates your executable program. So as we've already seen before, we can also do dynamic linking, so you can link modules at load time. Shared libraries on Linux would be an SO, on Windows it would be a DLL. This saves storage space on disk because you only have to supply each library once with the operating system. It saves memory in main memory because you only have to keep the code section of each shared library in memory once, and you can access it from all programs linked against, for example, your C library. So this was a method to make programs more efficient, especially on machines with not that much main memory and maybe not that much disk space. For embedded systems where you have your code in Flash, usually you don't use shared libraries just because you need to link everything statically anyways if you don't have an operating system available. So that was a very quick intro on compilers. Of course, this doesn't go into very much detail, so if you're interested, the next course you might take is my course on compiler construction, TDT 4205, and I'd be happy to see you there. And our next lecture, which will also be given by me, is going down one more step on our software architecture layer closer to the hardware. So we'll take a closer look at operating systems and give a quick introduction on how these works. work. So thanks for listening and hope to see you again next time. Bye.